Welcome to Paper 2 Foundation. First things first, write your name on the paper. Fantastic. The first question. When two magnets are close together, they exert a force on each other. What does the word exert mean? It means they put a force on each other. Complete table 1 to show if the magnets would attract or repel. Attract means pull together. Repel means push away from each other. If a south pole and a north pole are brought together, because they are opposite poles, they will attract. In the same way, the north pole and a south pole, since they are opposite poles, they will attract each other. Like poles repel, opposite poles attract. These are like poles because they are both south poles. Therefore, they will repel. These are like poles because they are north poles and they will also repel. For completing the table, you get 2 marks. If you get 2 or 3 correct, you'll get 1 mark. You won't get any mark if you only get 1 or 0 correct. Figure 1 shows the magnetic field around a bar magnet. A bar magnet is simply a rectangular magnet that has a north and a south pole. Which statements are true for the magnetic field shown in figure 1? We have to read all the statements first before we make our decision. The magnetic field gets weaker the further away from the magnet. The magnetic field is strongest at the poles. The magnetic field is uniform away from the poles. The magnetic field lines all meet at a single point, and the magnetic field lines point from south to north. Well, for this magnet, we can see if the magnetic field gets weaker further away from the magnet, because as we move further away from the magnet, the field lines, there are less of them. So that tells us the magnetic field does get weaker the further away from the magnet. The magnetic field is strongest at the poles. To check whether the magnetic field is strongest at the poles, we just have to see the density of the field lines. There are more field lines at the poles than anywhere else. So that does tell us the magnetic field is strongest at the poles. The magnetic field is uniform away from the poles. That's quite obviously not true, because you can see away from the poles they are at different densities. The magnetic field all meet at a single point. That's not true either. There's not a single point on this diagram that the magnetic field lines meet. And just from memory, we know that the field lines go from the north to the south pole. Figure 2 includes an electromagnet. Which metal is used to make the core of the electromagnet? This is something that we have to remember because we use ferrous metals for magnets, and aluminium and copper and magnesium do not fit. Only iron is used for the electromagnet core. Question 1.4. Complete the sentence. Choose the answer from the box. The switch is closed. There is a current in the what? If you look at the previous question, the coil is wrapped around the core. There is not a current in the core because the current passes through the wires. The core is not connected to the wires because the wires are insulated. So that's not our answer. Because the wires don't connect onto the paper clips, it's not the paper clips either. The answer is coil. 1.5. The number of turns on the coil is increased. The current remains the same. How does this affect the strength of the magnetic field around the electromagnet? One of the ways to make an electromagnet stronger is to increase the number of coils on it. That would mean the magnetic field would become stronger. The other answers, we don't have to entertain them. 1.6. The metal core was removed. The current remains the same. How does this affect the strength of the magnetic field around the electromagnet? Remember, the metal core is added so that the magnetic field lines all line up through the iron core. It makes the iron core an induced magnet. If I remove the iron core, the field lines aren't lined up perfectly, and therefore the magnetic field would become weaker if there was no iron core. Question 2. Hailstones are small balls of ice. Hailstones form in clouds and fall to the ground. Figure 3 shows different sized hailstones. Which force causes the hailstones to fall to the ground? There are 4 options, but let's have a look at the hailstone. There can be a force of weight acting on the hailstone, and then there is the force of any sort of resistance against the hailstone. The weight of the hailstone is what pulls it down. So which force out of these 4 causes the weight of the hailstone? It's obviously the gravitational force, because that's what pulls it down. 2.2. As the hailstones begin to fall, they accelerate. Which force increases the hailstone as the hailstone accelerates? Accelerate means speed up. If the hailstones speed up, then the air resistance increases. The faster it goes, the more molecules of air is colliding with the hailstones. And therefore, there is higher air resistance when the hailstone is faster. 2.3. After a short time, the hailstones fall at terminal velocity. Terminal velocity is when the forces acting on a moving object or a falling object is balanced out. Therefore, the downward force of weight is balanced out by the upwards force of air resistance. We say that the resultant force equals 0. Therefore, the question is, what is true at terminal velocity? If resultant force is 0, then it's not speeding up and it's not slowing down. It is moving at constant velocity. The answer that we can choose is that the resultant force on the hailstones is 0. Then a scientist investigated how the terminal velocity of hailstones varies with their diameter. Diameter is how wide the hailstones are, remember? Diameters we use in circles. So that's the diameter of a hailstone. The scientist said, is investigating that what happens if that diameter increases. In other words, what happens when the hailstone becomes bigger to the terminal velocity. Here are the results that they find. Question 2.4 says, estimate the terminal velocity of a hailstone with a diameter of 80 millimeters. Let's have a look at 80 millimeters. On the x-axis we see 80 millimeters, and 80 millimeters is right here. If I look up on that line, I should be able to find, the line that the scientist has drawn does not meet the 80 millimeters. So we need to extend their line so that it meets the line that we want to look at. This seems to be a proportional relationship, somewhat of a straight line, although it does have a slight curve to it. I'll take my pencil and I just extend that line out like that. Now, using a different color just so that you can see, I can mark where both lines intersect. It's at 45 meters per second as terminal velocity. And that's the answer that I write down on my answer line. Question 2.5. Give one reason why a hailstone with a larger diameter has a greater terminal velocity than a hailstone with a smaller diameter. Well, that's what we see from the graph, didn't we? We saw that when the diameter increased, that there was a larger terminal velocity. Why is that? Well, the terminal velocity, remember, is when weight and air resistance are equal to each other. Air resistance will be equal to weight when an object experiences a lot of air resistance. But for something like a hailstone, it's not going to experience a lot of air resistance. But it will still equal its weight if it's moving fast enough. If something has a higher weight, then it can accelerate to a higher speed before the air resistance balances out and the resultant force becomes zero. Therefore, the reason why something with a larger diameter has a greater terminal velocity is because the larger diameter hailstone has a greater weight. After falling, the hailstone hits the ground. Figure 5 shows the forces acting on the hailstone at the moment it hits the ground. Here's figure 5. 0.63 newtons are what is acting upwards. Only 0.15 newtons acting downwards. It asks, what is the magnitude of the resultant force on the hailstone? The resultant force, the result of the forces acting on it. To resolve forces, all you do is take one force and take it away from the other. 0.63, take away 0.15. You can do this in your calculator. However, I'm just going to do it on here. Look at that. My answer is 0.48. That is one of the options. Notice how, just to confuse you, they give you that as an option, which is right here, that as an option, which is right here, and that as an option, which is what would happen if you added both of those things up. 2.7. What is the direction of the resultant force on the hailstone? Well, the direction of the force is the bigger force take away the little force. That force take away that force. On the hailstone, the 0.48 is acting upwards. And that's all you write. Upwards. Question 3. The sun is at the center of the solar system. What type of object is the sun? The sun is a star. Just like all of the stars that you see in the night sky, the sun is also a star. Much closer to us. Next question. What is the name of the galaxy our solar system is part of? It gives us 4 names of galaxies. Although, I think these 2 names are just random. Andromeda is a galaxy. Sombrero is the thing that Mexican people wear. And a tadpole is a baby frog. Milky Ways are chocolate bars. But it is the name of our galaxy. I think it's a cool name that our galaxy is named after a chocolate bar. Or maybe it's the other way around. Table 2 gives information about some of the moons in our solar system. What is a moon? Well, for us, the moon is the big piece of rock that orbits around our planet. Lots of other pieces of rock orbit different planets. But the rock isn't the only thing that orbits our planet. We have man-made satellites that orbit our planet. A satellite is an object that orbits the planet. In this case, a moon is a natural satellite. Oops. Here's where we know if I've spelled satellite correct, because I'm going to check my spelling. had good reason not to doubt. In fact, I shouldn't have doubted myself. I think I've spelt it correct. 3.4. A student researched the radius of some planets in the solar system, and the radius of the largest dwarf planet is 11,190 kilometers. Radius of the smallest planet is 2,440 kilometers. Okay. The student made the following conclusions. That means they've come to these understandings. They said dwarf planets are always dwarf planets are always smaller than the moons. And number 2 is planets are always bigger than moons. Give one reason why each of the students' conclusion is wrong. There are 2 conclusions and 2 lines to draw answers from. So the first conclusion, dwarf planets are always smaller than moons. Is that true? Let's see. All we have to find is something that contradicts what he says here. So we look at the largest dwarf planet, which is 1,190 kilometers. And 1,190 kilometers is bigger than Charon. 1,190 kilometers is bigger than Charon. So we know that at least one of the moons is smaller than the dwarf planets. So he is wrong about that. That's what we write. We write Charon is smaller than the dwarf planets. Sorry, by the way, if anybody's mum is called Sharon. At least it's spelt differently. Number 2, planets are always bigger than moons. Well, the radius of the smallest planet is 2,440 kilometers. If there was a moon that was bigger than 2,440 kilometers, that will tell us that planets are not always bigger than moons. There it is. There are 2 moons that are bigger than the smallest planet. So the next thing that we write is moons Ganymede, I think that's how you say it, and Titan is bigger than the smallest planet. Planet. Taking care not to make any spelling mistakes. Excuse me if I have made any so far. Question 3.5. The Earth's moon and the International Space Station both orbit the Earth. Give one other similarity and one difference between the orbit of the Earth's moon and the orbit of the International Space Station. If you don't know, the International Space Station is a spaceship, if you will, that is orbiting the Earth, that contains people where people are living right now. It's a collaboration between the North American space agencies and the Russian and the Chinese space agency. So you'll have lots of different international astronauts living there. I think 6 at a time. This International Space Station is orbiting the Earth very quickly. So much so that I think it goes around once every 48 hours or something. I don't know. But it's much quicker than the orbit of the moon, because the moon takes 28 days to orbit the Earth. So, one of the similarities, or one of the differences, is how long the orbit is. Length of orbit. Or you could say speed of orbit. Why does the International Space Station take orbit very quickly? Well, it's much closer to the Earth than the Moon is, which is much, much further away. So we could also say height of orbit. All of those things are a good answer for the difference. What is the similarity? Well, the fact that they actually orbit the Earth in a circular pattern, because that is what an orbit is. Not all orbits are circular, however. For example, there is a slight elongation in the Earth's orbit around the Sun, and there's a very big elongation in Pluto's orbit around the Sun, for example. But for Moon and the ISS, the International Space Station, they both have a circular orbit. Next question. Very few people have been to the International Space Station. Suggest one reason why very few people have been to the International Space Station. Now, I'd love to go. However, I don't think I will be able to because it's very expensive. Unless people like Elon Musk and Richard Branson make space travel super accessible, all right, and they build a space station up there that people can go and visit, I don't think I'll be able to do it in my lifetime. But also, I don't think I'm trained for it. Astronauts train years and years to be able to go into space because it is dangerous and it requires training. Question 4. Figure 6 shows the weight of an orange acting from point X, or point labeled X. So that point right there. What is the name given to the point X? Well, point X is in the middle of the orange, and the orange is quite regular as an object goes. And the point at which all of the mass and the weight of the orange acts through is called the center of mass, or the center of weight. And that is point X for this orange. It's the center of weight. Why did I take the center of weight instead of the center of mass? Well, I can see the arrow for the weight drawn on it. That means it's talking about the force and not just about the particles. Therefore, it's the center of weight. Next question. Weight and mass are not the same, obviously. The relationship between weight and mass for an object can be written as weight, squiggly line, mass. Which sentence describes the relationship between weight and mass? It's only asking you, what in the world does this line mean? It means whatever's on this side, I'm going to say X, is directly proportional to whatever's on this side. This line is a symbol for direct proportionality. So we take that. Next one, figure 7 shows a balance used to measure the mass of 5 oranges. All 5 of the oranges have the same mass. Determine the mass of just one orange. Okay. Let's read the scale. This scale starts off at 0, ends at 5, and it's measuring in kilograms. After 1, the arrow is actually pointing to the next line after 1. So we need to know what each small line means. There is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 small lines between 0 and 1. So each small line represents 0.1 kilograms. Since it's pointing at the line after 1, we know the mass of 5 oranges is 1.1 kilograms. But mass of 5 oranges isn't what the question asks. It asks the mass of just one orange. All I have to do is take 1.1 and divide it by 5, which gives us the mass of one orange to be 0.22 kilograms. I've obviously done this before. That's why I got the answer so quickly. But if you're doing it for the first time, you'll need one of these. 1.1 divided by 5 is 2.2. Oh, 0.22. This working out that I've done here should actually go on this line. I've written it here just so you can see it clearer. Next question. It's really easy. Calculate the weight of 1 orange. It says gravitational field strength is 9.8 newtons per kilogram. And it tells us to use the equation weight equals mass times gravitational field strength. Let's make it easy for ourselves and write down everything that we know. Do we know the weight? No, we don't. That's what we're trying to calculate. So I'm going to put a question mark underneath that. Equals, do we know the mass? What do we need the mass of? Well, just 1 orange. Yes, we do. We just calculated it. 0.22. Times by gravitational field strength, which has been given in the question, is 9.8. Now, we write out everything inside the equation. If there is a question mark next to something that we don't know, we write out the word or the symbol again. Weight is equal to 0.22 times by 9.8. Fantastic. Let's put this into our calculator. I've done this already, but I'm going to show this to you. 0.22 times by 9.8, and it usually gives me an answer as a fraction. That's not very useful, so you need to know the number or the button that changes fractions into a decimal in your calculator. Once I press that button, the answer pops out to be 2.156. 2.156 is the answer we write down. Just to check, it doesn't tell us to give it to any decimal places or anything, so we don't need to round it. Next, the balance shown in figure 7 contains a spring. The spring is what measures the extension, or the spring is what measures the weight. Figure 8 shows a spring with no force acting on it and with a force of 6 newtons acting on it. What is the extension of the spring when the force of 6 newtons is acting on it? It's asking us to calculate the extension. How much does the spring change by? It starts off at 5 and it ends up at 3.5. 5 take away 3.5 will get us the answer of 1.5 centimeters. But let's have a look. All of these answers are in meters, so I need to convert from centimeters to meters. How do we do that? Well, there are 100 centimeters in 1 meter. To go from centimeters to meter, I need to divide by 100. 1.5 divided by 100 can be done on the calculator, but because I can divide by 100 in my head, just by moving the decimal place 2 places, I can write 0.015 as my answer. Right there. How easy is it that we've got a tick box to do that? 4.6. Calculate the spring constant of the spring. Use this equation right here. The spring constant of a spring is force divided by extension. Again, we write down everything that we know and everything that we don't know. We've been asked to calculate spring constant. Do we know the force? Yeah, because it says in the previous section that the force applied on the spring is 6.0 newtons. Do we know the extension? Of course we do. We just did the right answer and we got 0.015 meters as my extension. All we have to do now is plug those numbers into the equation. We write out what we don't know again. Spring constant is equal to 6 divided by 0.015, which gets us an answer of, now you know that you can do this in your calculator, but I've already done it, is 400. If you've written all this that's been circled in blue, you normally get a mark. That's why we don't just go for the answer line. We write out everything that we're thinking, so that even if we mess up, we get it right. What will happen to the spring when the force is removed? That's a good question. What should happen to the spring when the force is removed? A spring can be elastically deformed. That means I can stretch it, and when I let it go, just like an elastic band, it goes back to its original length and shape. So that's what we write. We write that it returns to its original length and shape. Number 5. Let's go. Here we have a question about the electromagnetic spectrum. Ultraviolet and visible lights are both part of the electromagnetic spectrum, and instead of highlighting it, what I've managed to do is cross it out. There we go. So this question is about the electromagnetic spectrum. How does the speed of ultraviolet in a vacuum compare to the speed of visible light in a vacuum? Well, if they're both part of the electromagnetic spectrum, we know that their speed in a vacuum is the same. Easy. Figure 9 shows parts of the electromagnetic spectrum. Radio waves, A, B, C, D, X-rays and gamma rays. Which letters represent the position of ultraviolet and visible light? Well, this question is asking us to remember the order of the electromagnetic spectrum and equate that order to these gaps that they've put in. There's always a mnemonic to learn the electromagnetic spectrum. The one that I use is too rude, and a student taught me that. But I'm going to try and find one that's a little bit less rude. Real men in violet underwear, extremely gorgeous. That's a bit weird. RMIVUXG. These are the first letters of the parts of the electromagnetic spectrum. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. So which represents ultraviolet? It's D. Which represents visible light? C. There we go. Table 3 shows the range of wavelengths for different types of ultraviolet. Type: ultraviolet A, ultraviolet B and ultraviolet C are called UVA, UVB and UVC, and the range of wavelengths are given in the table. Determine, which means, quite quickly, determine means find out. Which type of ultraviolet shown in table 3 has the largest range of the wavelengths? That's quite easy. To gain full marks, you must be able to calculate the range of wavelengths for each of the ultraviolet. So we have to do the calculation for all 3 and then say which one has the largest range. If we remember from maths lessons, to calculate the range, you have to take away the highest value and the lowest value. Thankfully, the highest and the lowest value are given here. It goes from 315 to 400. So UVA. 400, take away 315 will give you 85. I'm doing this on a calculator, but I'm just doing it quickly for you. UVB. 315, take away 280 gives you 35. UVC, 280 take away 100 will give you 180. It's quite easy to see that this answer has the largest range. Next one. Figure 10 shows how different types of ultraviolet are absorbed by the ozone layer in the Earth's atmosphere. Table 4 shows the relative ionizing power from each type of ultraviolet. Explain the importance of the ozone layer in reducing the risk to people from all types of ultraviolet. Use figure 10 and table 4. Here it is. Let's do it. The ozone layer clearly does not stop any UVAs because 100% of the UVAs get through. It clearly does stop most of the UVBs because only 5% get through. None of the UVCs get through, which means ozone layer does a good job of stopping all of it. The question is, explain the importance of the ozone layer in reducing the risk to people from all types of ultraviolet. Well, what is the risk of ultraviolet radiation hitting you? Well, ultraviolet radiation can cause damage to the skin cells, can lead to skin cancer, can cause sunburn, and if you look at it, can damage your eyes. Which one does it most? Well, the highest ionizing power one will do it the most. UVC has the highest ionizing power, so that's the one most likely to damage you. However, UVC is completely stopped by the ozone layer, so ozone layer does a good job for that. That's the first thing that I'm going to write down. Ozone layer absorbs all of UVC, and UVC is the most dangerous. Dangerous. The next thing that I need to write down is ozone layer absorbs nearly 95% of UVB. Some people are thinking, where did Mr. Valuran get 95% from? 100% take away 5% is 95%. And UVB has a medium risk. Why is it a medium risk? Because it's medium ionizing power. Then the ozone layer does not absorb any UVAs. But thankfully, UVA is not dangerous. How do we know that UVA is not dangerous? Because it's the least ionizing power. Fantastic. The greater the ionizing power, the greater the risk. We have to let the examiner know that. I'm just going to do it in a different color for fun. Greater the ionizing power, greater the risk. Okay, so what are the risks? UV damages skin cells, could cause cancer, it could damage eyes, could cause sunburn, there we go. All of these are the risks. You need to write down every single thing to get all 4 marks. Fantastic. 5.5. The sun emits visible light. A student concludes that visible light is not absorbed by the ozone layer. Give one piece of evidence that shows the student's conclusion is correct. Well, what's the piece of evidence to show that the ozone layer does not absorb the visible light? If the ozone layer did absorb the visible light, would we be able to see the sun? No. So, because our eyes detect the visible light, we know that at least some of it gets through. From the sun. Next question. Figure 11 shows white light incident on a color filter. Complete the sentence. Choose the answers from the box. White light is coming in and only blue light is getting through. So what type of filter is it? It's a blue light filter, or a filter that only lets blue lights through. It's probably a piece of plastic that is blue colored that absorbs every other wavelength of light except the blue, and that goes through. When white light is incident on the filter, only blue light is what? What is the word for when something goes through? It's not absorbed, not radiated, not reflected, not refracted, it's transmitted. And all of the colors are stopped. So what's the word that means stopped? Absorbed. The Earth is surrounded by an atmosphere. The radius of the Earth is 6,400 kilometers. Which of the following could be an approximate depth of the Earth's atmosphere? This is a tricky question. This is an approximate depth of the Earth's atmosphere. Is it 100 kilometers? Is it 6,400 kilometers? Is the atmosphere as wide as the Earth is round? Is it 100,000 kilometers? Or is it 640,000 kilometers? If we think about it, this is the Earth, and in orange I'm drawing the Earth's atmosphere. It's very close to the Earth. It's not more than 100 kilometers, is it? What state of matter is the most of the Earth's atmosphere in? That means the air that we breathe is the Earth's atmosphere. What state of matter is it? Is it a solid, liquid, or a gas? It's a gas. Figure 12 shows the atmospheric pressure varies with the height above sea level. If the height above sea level increases, then the atmospheric pressure in pascals decreases. The height above sea level is in increments of 200 for every big square. That'll come in handy in a minute. The question is, the highest point above sea level in England is the top of a mountain called Scafell Pike, and Scafell Pike is 978 meters above sea level. You have to determine, which means find out, the atmospheric pressure at the top of Scafell Pike using figure 12. 978 meters. Where is 978 on this graph? We know that going from 0 to 200 there are 10 little tiny squares. So each tiny square, and I'm going to try and color that tiny square in orange, each little tiny square is actually only 20 going that way. When we get to a medium square, and I'm going to do that in blue, that is 100. So each big square is 200. Going from 800 to 1000, somewhere in the middle, right here, is 900. Then we need to get to 978. 920, 940, 960, 980. Uh-oh, we went a little bit too far, but 980 is the nearest that we've got. Then we right up until we meet the line there. And when we meet the line, we move across, and I'm going to mess this up because I don't have a ruler. And we get to here. 90,000. That is the height above sea level. Now, obviously, there is a bit of a give here. For example, if you don't put your ruler quite straight, or if you don't put it on 978 quite correctly, there is a small range that you can get it wrong in. But realistically, you can't get this much wrong. 90,000 is the answer that I put here. 6.4. Determine the difference between the atmospheric pressure at sea level and at the top of Scafell Pike. Use figure 12 and your answer from question 6.3. The difference in the atmospheric pressure at sea level and at the top of Scafell Pike. At sea level, which is 0, the atmospheric pressure is almost close to 100,000 and something. So let's see what each little square represents. Going from 100,000 and 100,000 and 100 and 2,500, we know that 10 little squares represents 2,500. So dividing that by 10, each square represents 250. So 100,000, 250, 100,000, 500, 100,000, 750, and 100,000, 101,000. So at the sea level, the atmospheric pressure is 101,000. I'm muddling my words because there's a lot of ones and 100s right there. And then we have at the top of Scafell Pike the answer that we've already calculated, which happens to be 90,000. Take away this, should get us the answer of 1,000 should get the answer of 11,000 as our difference between pressure. A student climbs Scafell Pike. Why does the atmospheric pressure decrease as the student climbs higher? Well, going to the top of Scafell Pike, you will find that there is less particles of air there compared to the bottom at sea level, where there's more particles of air. If there's more particles in a given volume, then we say that air is dense, that air is less dense. So one of the reasons why the atmospheric pressure decreases as the student climbs higher is because the density of the air decreases. If there's less particles, the air clearly exerts less force on the student, so that is wrong. If there is less particles, then the mass of air above the student decreases. The temperature of the air actually decreases. That is why that is wrong. Because as you know, if you go to the top of a mountain, it becomes colder. And the volume of the air above the student decreases. There's less particles. 6.6. Figure 13 shows a mountain lake. The lake has a surface area of 2,000 meters squared. Atmospheric pressure exerts a force of 188 million newtons on the surface of the lake. 6 zeros is A million. Calculate the atmospheric pressure on the surface of the lake. It gives us an answer. All you have to do is plug your numbers in. Pressure, we don't know. Area, we do, which is 2,000. Force is 188,000,000. Pressure equals force divided by, we do know force, so we can plug that number in. 188,000,000 divided by 2,000 gives us an answer, once I've plugged this into my calculator, of 94,000. Awesome. Sound travels as longitudinal waves. What does that mean? It means that the particle oscillations are along, parallel to the direction of energy transfer. Complete the sentences. The distance between the center of one compression of a sound wave and the center of the next compression is called the what? What do we mean by compressions? In a sound wave, because the particles are pushing in and out, vibrating, you'll find areas of compression where the particles are pushed close together and areas of rarefaction where the particles are spread apart. We usually draw this like lines. Now, I haven't done a good job of drawing this. Hopefully, I'll be able to explain this without the best drawing in the world. But, as you can see, these are the areas of compression where the particles are squished close together. And there are areas of rarefaction where the particles are further apart. This does not look like the typical wave that we draw, but something like this is the typical wave that we draw. We know that the distance between the trough or the peaks is the wavelength of the wave. In the same way, the distance between the two compressions is the wavelength of the wave. That symbol lambda is for wavelength. So our answer, the distance between the center of one compression of a sound wave and the center of a next compression is called the wavelength. The number of waves passing a point each second is called, that's easy, frequency. Lots of waves passing a second, high frequency. 7.2, complete the sentence. Choose from the answer box even. In a longitudinal wave, the oscillations, that means the vibrations, are something to the direction of the energy transfer. Are they perpendicular? Do the particles move up and down? Or do the particles move back and forth? They move back and forth. They are parallel to the direction of energy transfer. 7.3. A sound wave has a frequency of 8 kilohertz. Which of the following is the same as 8 kilohertz? The question is asking you to convert from kilohertz to hertz. Kilohertz to hertz. 1 kilohertz is equal to 1000 hertz. to do that. So to go from kilohertz to hertz, I have to times by 1,000. Which number is 8 times by 1,000? It's 8,000 hertz. Easy. Next question. Calculate the period of a sound wave with a frequency of 8 kilohertz. Use the physics equation sheet. To do this, you need to write down that 8 kilohertz is actually 8,000 hertz. Then, in the physics equation sheet, you need to find the equation that has time period and frequency in it. The equation that we need is time period is 1 divided by frequency. We plug our numbers in just like normal. Time period is equal to 1 divided by 8,000, which gives us an answer of 0.000125 seconds. And that's what we write down on the answer sheet. Answer line 0.000125. Next question. Calculate the wavelength of a sound wave with a frequency of 6,600 hertz. Use the speed of sound, which is equal to 330 meters per second, and it gives us the equation very kindly. And it also asks us to choose the unit from the box. Remember, it's wavelength. So we're looking for something that measures length. It's not newtons, it's not kilograms, it's going to be meters. At least we've got 1 mark already. The next mark is for putting everything that we know into this equation. Frequency goes here and speed goes here. Wavelength is equal to 330 divided by 6,600. Remember, just for writing this substituted equation, we get a mark. Once we do that, plug it into our calculator, we get 0.050 as our answer. Next question. Figure 14 shows the arrangement of 2 loudspeakers at a concert venue. Distance A is, I'm going to mark that as red. Distance B, I'm going to mark as blue. The loudspeakers in figure 14 are tested by playing the same song through both loudspeakers. A sound technician listens to the songs. Use the physics equation sheet to answer the question. Write down the equation which links speed, distance, and time. Speed is equal to distance divided by time. That's something that we need to remember. But it's in the equation sheet as well. V is equal to S divided by T. Next, we're probably going to have to use that equation. Distance A on figure 14 is 13.2 meters. Awesome. And the speed of sound is 330 meters per second. Calculate the time taken for the sound to travel from loudspeaker A to the technician. Write down the equation that we've just written down, which is speed is equal to distance divided by time. Now we need to substitute our numbers. We know the distance, which is 13.2. We know the speed. Distance, speed. So let's plug those numbers in and then leave time on its own for now. 330 is equal to 13.2 divided by time. To get time on its own, we need to rearrange this equation. Timesing by time on both sides and dividing by 330 on both sides is usually how people do it. I will show you how to do that. It times by time on both sides, which obviously cancels this out. you divide by 330 on both sides, which obviously cancels that out, which gives you with your new equation, and I'm going to do that in blue, it's time is equal to 13.2 divided by 330. Plugging that into our calculator, we should get an answer of 0.04 seconds. The sound from each loudspeaker travels at the same speed. Okay. For the sound technician to hear the song clearly, the sound from loudspeaker B should be emitted slightly before the sound from loudspeaker A. Explain why. Well, because loudspeaker B is further away, there is a longer distance to travel, so if it's all going at the same speed, it should get a head start. And that's what we need to write down. Loudspeaker B is further away from the technician. That's how you spell technician. That's how you spell technician. Than loudspeaker A. So the sound would take longer to travel. To the technician. Therefore, so it needs more time. So that why do we need to give it more time? So that both sounds arrive at the technician together. The technician needs to be able to hear both of those things together in sync. That's why loudspeaker B needs to be earlier than loudspeaker A. Figure 8. Fantastic. Is that my car? The battery in an electric car needs to be recharged. Suggest 2 factors that affect the distance an electric car can travel before the battery needs to be recharged. 2 things that affect how long you can drive your electric car for before you can recharge it. Well, one of the things that affect it is how big the battery is. The complicated word for how much charge a battery can hold is the capacity of the battery. But what else affects how quickly the battery runs out? Well, on your phone, how much you use it tells you how quickly it runs out. For example, if you were playing videos or video games, that will run down your battery quicker than if you were just having it idle. So in a car, what does that mean? The speed of the car affects how quickly the battery runs out. The speed at which you use it. How big the car is. The mass of the car. How many people are in the car? Maybe the weight of the car. Whether it's going uphill or downhill. Is it stopping at traffic lights? Lots of things affect how quickly the battery runs out. Use the physics equation sheet to answer questions 8.2 and 8.3. Write down the equation which links acceleration, change in velocity, and time taken. Using the equation sheet, we know that acceleration is change in velocity divided by time taken. This little symbol is delta, which means change in. The maximum acceleration of the car is 20 meters per second squared. Calculate the time for the speed of the car to change from 0 to 28. Well, that is change in velocity. That is my acceleration. So we plug all of these into my equation. 20 is equal to 28, because 28 minus 0 is equal to 28. That's change in velocity, remember. Divided by time taken. Remember, now we've got that equation where I need to rearrange it. I've shown you how to rearrange before, but I can do it again. It's times by t on both sides. So that cancels out. Divide by 20 on both sides. So that cancels out here. So that's t is equal to 28 divided by 20, giving you an answer of 1.4 seconds. We're nearly coming to the end. We've only got one more question left. Let's finish 8.4. In a trial run, the car accelerates 10 meters per second until it reaches its final velocity. Okay. Distance traveled by the car is 605 meters and the initial velocity of the car is 0 meters per second. Calculate the final velocity of the car. While using the physics equation sheet, I can find something that has initial velocity, final velocity, acceleration, and distance all in one. The equation that I use is v squared minus u squared is equal to 2as. V squared is final velocity, u squared is initial, 2 acceleration, s is distance. What is v squared? What is v squared? The final velocity. Oh, that's what we're calculating, so we put v squared. U squared is, well, 0 squared. Doesn't matter. 2 times acceleration is 10 times by s, which is 605. V squared, that obviously cancels out, is equal to 2 times by 10 times by 605, which is v squared is equal to 12100. Therefore, v is equal to the square root of 12100, gives us an answer of 110 meters per second. 110 there. Jolly good. 8.5. Use the physics equation sheet to answer questions 8.5 and 8.6. Write down the equation which links distance, force, and work done. Work done is force times by distance. When traveling at its maximum speed, the air resistance acting on the car is 4,000 newtons. That's my force. Calculate the work done. That's my W. Against the air resistance when the distance that the car travels is 7.5 kilometers. Kilometers, oh no, that's not the standard unit that we want. We need to change that to meters. So the first thing to do is 7.5 kilometers is equal to 7,500 meters. As we go from kilometers to meters, we times by 1,000. Now, plug all the numbers in. Work done. That's what we're trying to calculate. Force is 4,000 times by distance, which is 7,500. 4,000 times by 7,500 is 30 million. What? Doesn't that seem a little bit too big? Let me just plug all that into the calculator to find out. 4,000 times by 7,500. Oh wow. Seems the calculator says is right. So 30,000,000. Jolly good. 8.6 done. 9. A student used a ray box to shine a ray of light through air into a glass block. The student investigated how the angle of refraction varied with the angle of incidence. Table 5 shows the results. Here's the angle of incidence, here's the angle of refraction. When the angle of incidence was 10, the angle of refraction was 5, and so on and so on and so on. Okay, before we do this question, I need a quick costume change. See you later. Describe the method the student could have used to obtain results in table 1. Your answer may include a label diagram. They're asking us to do the diagram for and the steps for the refraction practical. I'm going to do a step-by-step, and each of my corresponding step will refer to a part of the diagram, so that way you can follow along really easily. I'm going to try and keep it all on one page here. So the first step to do a diagram, to do the practical, is place glass block on paper and draw around it Okay, that's my first step, so I'm going to just do the diagram for that, and I'm just going to label it 1. Number 2 is use ray box to shine the light through glass. Okay, so here's my diagram of the ray box. That's number 2. Number 3 is to mark the ray of light entering the glass block. Okay, so this is number 3. So this is the ray of light that is entering the glass block at this point right here. Number 4 is to mark the ray of light emerging from the glass block. Okay, so if this is the ray of light entering the glass block, somewhere over here will be another ray of light emerging from the glass block. Okay, so that is number 4. Number 5 is to join this point and this point up. Join the points to show the refracted line. Okay, so I'm going to use a darker blue here. Join these points. That shows the refracted ray, and I'm going to label that number 5. Number 6, I'm going to do it in a different color. I'm going to do it in a purple, because number 6 is to draw the normal line. And the normal line is 90 degrees to the glass block, where the incident angle, the ray's incident. So I'm just going to do the normal line, which is going to be, that's terrible, but just imagine it's 90 degrees and correctly drawn with a pencil and a ruler. Remember, the normal line has to be drawn as a dotted line. Okay, so next I'm going to do it in a different color still. So I'm going to use a protractor to measure the angle of incidence. So this is the angle that I want to measure using a protractor, and that is number 7. Number 8, probably worth doing in a blue, just so we can stand out. Number 8 is use a protractor to measure angle of refraction. That is this angle right here. Okay, so that is number 8. Okay, now that you measured both angles, you just need to play about with it to vary it about. So number 9 is let's call this a 9-step method. Right, number 9 is vary the angle of incidence in increments of 10 degrees from, if we have a look at the table, it's from 10 degrees to 80 degrees, and record the angle of refraction on a table, and we produce the table that is in the question. Okay, this is a 6 marker. I've put 9 points on there. Alright, the points of just drawing the sort of refraction is sort of 1 to 6. The measurement is 7, 8, and then making the table is step 9. Just to vary it up, I've used loads of different colors. Some people should really like that. Next question. Okay, so I've got the one that I've already done before. Next question is, Figure 2 is an incomplete graph of the results. Complete Figure 2 using data from Table 1. Label the axes, plot the remaining data sets. Draw a line of best fit. This is so easy. Alright, so we just got to get our table, which I've screenshotted here, using a pencil and a rule. A sharp pencil. We have to mark these data points. I'm going to do it in a bright red color so you can see, but obviously you're going to use your pencil to do this. So we've plotted up to 30. 40 degrees is 19. So 40 degrees is 19. As I look, I can see that each little square is 1. So 15, 16, 17, 18, 19. Small x marks the spot. 50 degrees is 23. 21, 2, 3. 60 degrees is 26. 25, 26. 70 degrees is 28. 26. 27, 28. And 80 degrees is 20. 80 degrees is 29. Okay, I think what's happened here is because this little screenshot here is covering up some of the axes, you can't see the rest of the numbers, but oh well. So we've plotted that. Let's draw a line of best fit. Our line of best fit is going to be, well, you can see it's curving, so let's just draw a curved line of best fit, going through as many points as possible. Freehand line, just like that. And that's what your line should look like as well. You don't need to draw it with a ruler, you're drawing it with a freehand. Okay, now let's label these axes. So the axis on the left is angle of incidence, angle of refraction in degrees, angle of refraction in degrees. Then this is angle of incidence in degrees. Why was I so sure of that? Well, I just looked at the table, the headings, and just plotted it as it is. Alright, here we go, underline it just to make sure. Next question. Complete the ray diagram in figure 3. Show the reflection of light from the surface. You should draw the normal line and draw the reflected ray. So it's 2 marks for getting these 2 things done. The normal line, remember, is 90 degrees to the surface, and you have to draw it exactly where the angle of incidence is measured from. So right here is our normal line, and we draw that as a dotted line. Okay, remember you'll do this with a pencil and a ruler, and it will be exactly 90 degrees. Make sure it's 90 degrees from the mirror. And then what you have to do is measure this angle. Okay, I don't know what it is, I haven't measured it, so whatever that is has to be exactly the same angle as you draw it here. So I'm going to put that as X, and this has to be X as well. You don't have to draw the arrow it says on the mark scheme, but it's always good to show that the arrow is going out because it's reflecting away. Some mark schemes do ask you to do that arrow, by the way. Next question. The student investigated the reflection of a light by a plane mirror. Explain the two ways that method A is better than method B. That's really easy. You can obviously see the method A is better because the protractor is on the mirror, just underneath it, so you don't have to move the protractor around for you to be able to measure the angle of incidence and the angle of reflection. The second reason is that you can see that the laser that they're using is a fine, thin sort of line, whereas the ray box, as you'll remember, will produce a ray of light that diverges. So, two marking points. The first one is protractor on the mirror. So you don't have to move it. Okay, so that's the good thing. Why is that useful? Because so you can measure the angles correctly, or more correctly, I was going to say, but better. And number two is ray is thinner. Alright, so a laser and no or less diverging. We can say does not diverge. Does not diverge. Why is the fact that it doesn't diverge easier? Making it easier to judge the center of the ray, because we're measuring the angle of incidence and the angle of reflection from the center of the ray. Now, just to make it clear, when we do this practical, we'll end up having to choose where that middle is, and we'll probably end up drawing a line sort of like this. Now I've done it really badly, but where the angle of reflection is measured from, because it's such a thick line. Whereas for a thin line, super easy, you're just looking at the protractor to find out.